Go for it.
Okay, so good afternoon, everybody. Before we start, I would like everyone to keep their mics unmuted during the talk. Welcome to the first colloquium of this semester, titled Directly Detecting Dark Matter by Kimberly Palladino. Her undergraduate work was done at Princeton University, where she worked on cosmic microwave background experiments. And then she completed her PhD at Ohio State University on a neutrino astronomy balloon experiment called ANITA. She did her postdocs at Massachusetts Institute of Technology on the dark matter experiment MiniClean. And then she was a research scientist at SLAC in Sudbury, Ontario, and later at the SLAC National Accelerator Laboratory when she switched to the dark matter experiments LUX and LZ. She was a faculty member at the University of Wisconsin-Madison for 5 years prior to her joining Oxford University this summer. She is currently the physics coordinator for the LZ Direct Dark Matter experiment. And we welcome Professor Palladino, and whenever you're ready, Professor.
Gracias por haberme invitado a la Coloquio. Buenos días a todos. Estoy muy contenta de hablar con ustedes hoy. Admito que estoy avergonzada que no les presento mi charla en español, porque mi mamá era una profesora de español. Así, sigo en inglés. Gracias. So this is a picture of our photomultiplier tube array for the LZ experiment that's under construction and commissioning right now. And I'll be talking about it in the bigger context of looking to directly detect dark matter. So astrophysics gives us the evidence for dark matter existing. And there are four main I think pillars, although many other pieces of the puzzle also holding it up. So the first is in this top left plot, where we plot velocities of, say, stars as a function of distance from the center of a galaxy. And this is the M33 galaxy. And it's these velocity distributions that first, when looking at the coma cluster, gave Fritz Zwicky the idea that there had to be something like dark matter. And this is what the astronomer Vera Rubin got a lot of credit for studying in the 1960s. That what we'd expect from looking at where the luminous matter of a galaxy is something like this orange curve, but what is seen is something like this green curve. And when the velocities stay high out to large radii and even increase, that can really only happen if there's still mass going out to those distances. But we don't see much mass that's making light. There's no big stars. We're not near the arms of the galaxy anymore out there, but there's still more stuff. Now from just this picture, like, oh, that's unexpected, but you could still explain it with things like modifying Newtonian gravity, just having normal mass that's not making light. So you can think of it like brown dwarfs, you know, stars that never quite turned on. And so you don't, from this picture alone, have a fundamental problem with physics. But if you go over to the top right, here's another very visual picture of why things are unexpected. And this is the bullet cluster. It's collisions of actually two clusters of galaxies. And it's got some artificial coloring on it, where the red is hot gas that's giving us X-ray emissions. And in blue, using gravitational lensing, they've mapped out where the actual matter of those colliding clusters of galaxies are. And we see that they're not in the same place. As things collide, the gas hits other gas, gets heated up, and emits light. But the main bulk of the matter is in dark matter, and it just goes through unimpeded. It's not getting warmed up by hitting other regular matter. It's not getting warmed up by hitting other dark matter. And so this is not anything we have a model for in our standard physics. Now, these are great visuals, but for more of the precision of how much we know about dark matter, we look to some other astrophysical evidence. Down in the lower left is the spectrum of the cosmic microwave background. And along the x-axis is this multipole moment that's a measure of, angular distance on the sky of how points are correlated. So how big a different blob of correlated energy or temperature or initially density in the universe at the time the cosmic microwave background light disassociated from our normal matter. And, this is not what I'm an expert in. I don't want to delve too much into this, but the important things is that the locations and heights of the additional peaks clue you into how much matter there is in our universe. And so we say that we've got essentially a flat universe. We've got just enough matter density to keep our universe expanding. It's not going to contract back, and it's not going to fly apart extra wildly. But to make up that total mass, we need a significant amount of it to be dark matter, and not our normal matter, not things made of protons or neutrons or atomic nuclei that we're used to. Another nice picture that can also, in the end, be quantified by others is on the right-hand side. And there's actually 4 different pictures here. 2 are simulations and 2 are data. And from just looking at them, you can't tell which is which. And that's exactly the point. That when we map out our galaxy with these large-scale sky surveys, we see this large-scale filamentary wall structure in our universe. And if we run a simulation, you can essentially reproduce that if you have a simulation of just dark matter, which in this case is just a particle that only interacts via gravity. And if in fact you add the other regular forces to it, if you have normal matter and you evolve a picture, you don't get the same structure that we see right now. It's only when you start to get to structure smaller than the size of a galaxy that all the rest of the normal physics we're used to, electromagnetism and the nuclear forces, come into play. So at the big picture of our universe, the thing that matters the most is dark matter. So this is what astrophysics tells us, that we are looking for something that dominates gravitationally. It doesn't interact with the electromagnetic force. It's not making any light. And there's a lot of it. But we're not really told much more about what it is. So when you become a dark matter physicist, you officially solemnly swear to always show a pie chart about what our universe is made up as. And so this is one of my favorites, seeing that it's dominated by something else called dark energy. This is something even crazier than dark matter. If you really want to understand the mysteries of our universe, this is a place to go after. But the people who do that are astronomers. And as you'll see, I like to build a different type of detector and have kind of a crazy work life. And so I didn't want to be an astronomer. So I went for the next biggest pie piece, this dark matter one. Everything else that we know about in the universe is only about 5% of the universe. And most of that is just free gas of hydrogen and helium. Then, when hydrogen and helium collapse down, we get stars. We also have neutrinos, and then all the rest of the heavier elements, which are what, of course, dominate our lives here on Earth. So what could this dark matter be? Well, we now have candidates that cover over 90 orders of magnitude of what it could possibly be in the mass of the new particle or wave-like thing when you start talking about very low energies of what it could be. And this picture has really advanced in the last decade or so. And so what I'm going to be focusing on today is really just this category of WIMPs, weakly interacting massive particles, which are one of the longest lasting models for what dark matter can be, and one of the most well motivated models. Now, if you think these names and lists are a little bit crazy, so do I, and so does Randall Munroe, the cartoonist behind the XKCD comic strip. And so he has one about dark matter candidates where there's a whole bunch of the real ones, but space cows and bees and other humorous options thrown in. So how are we going to look for a weakly interacting massive particle? Well, we can do it in a few different ways. If you're used to particle physics and thinking about Feynman diagrams, which as a drawing can encompass all of the math of particle physics, one of the great joys of us not knowing what dark matter is that we get to make a fake Feynman diagram. And so here the X's or chi's are our dark matter particle. SM stands for a standard model particle, and somehow they're going to interact with each other, and we don't know what that is. So if you read this plot going from top to bottom, you would have dark matter coming together and annihilating and making some normal stuff. And some of that normal stuff could be neutrinos or gamma rays or electrons and positrons, the anti-electron. And you would see this happening in places where there's a lot of dark matter out in the galaxy. And so this is what we call indirect detection. And astrophysicists have numerous different ways to look for such signals. If instead I read this from the bottom up, I can collide together standard model particles, like in a collider, and hope that they had enough energy to make dark matter. And then the dark matter or the mediator, the thing that's within that circle, would be produced, would fly out of the detector, and you would know that you made something that disappeared, and that could be dark matter. Theorists, of course, are giving us a lot of different options for this, for all of these things. And what I'm going to really be focusing on today, is if we read it going from left to right, where we have dark matter and normal matter bump into each other, the dark matter bounces away, and because we saw some normal matter get hit, we know that nothing else could have hit it, that we built a really pure detector that is shielded from all other regular radioactivity that we're used to with particles bouncing around, then if we eliminate all those other options, then we could say, aha, it got hit by dark matter. And that's what we call direct detection, and it's a scattering experiment. So that's what I do. And as a joke, people have realized that the field could be just simply called the options of make it, break it, or shake it. And I wanted to really add that the theorists are the bake it, the people who are making up ideas to add to the rhyme. So I've used this word WIMP a few times for weakly interacting massive particle, but what actually is it? So the idea arrived as people realized that particles with masses of about 100 GeV, so 100 times the mass of the proton, but very kind of central on the weak energy scale. And if they had interactions at the weak scale of the interactions of the W and Z bosons, then if we start with the model as shown on the right, where early in the universe, there's lots of energy, it's hot, and particles are popping in and out of existence. And as the universe cools down and expands, two different things happen. The first is that we stop having enough energy to make new dark matter. And so our relative abundance, starting from our maximum of just 1, starts to decrease as a function of time. And then eventually, not only is the universe cold enough that we're not making any more dark matter, but now all the dark matter gets spread out from the other dark matter and can no longer annihilate and turn into something else. And we just get locked in for a particular abundance or a particular density of dark matter. And then that essentially remains the same from that point in the early universe to today. And these weak scale masses and cross sections would give us a dark matter density of 0.3 GeV per cubic centimeter, or a third of a proton per cubic centimeter of mass. And that's exactly what we measured today. So, we're looking for something at a weak scale, and it gives us the density we've got today. Those two things aligning are what is called the WIMP miracle. And unfortunately, that very simple idea has been ruled out over 20 years ago. But it turns out particle physics isn't that simple. There's a lot more ideas that with really common sense tweaks to that idea still really fit the idea. So there's ideas of supersymmetry, where there can be a new lightest supersymmetric partner of our regular particles, and it could do this. Instead of interacting with the weak scale bosons that are mediators for forces, that could actually interact via the Higgs boson that everyone's so excited from the LHC. And so probing those different types of interactions are what people like me who are looking for direct detections of WIMP dark matter are looking for. The other reason WIMPs are great is that the name was in contrast to the option of MACHO, which stood for Massive Compact Halo Object. And that would have been something like a star that didn't turn on. And those have been ruled out, but it was really nice that our field was MACHOs versus WIMPs, and the WIMPs won. So this is the idea of a WIMP, and we're going to be talking about direct detection. So what do you actually need to do your direct detection? Well, you have to be able to see those really low energy WIMP-induced recoils, which means we need a really radiogenically pure detector. We can't have lots of gamma rays, electrons, neutrons, alpha particles bouncing around and bumping into our particles. And we need to have a really low threshold of energy. So in the tens of keV, and really nowadays much lower than that, to be able to see these signals. And in general, we want the ability to distinguish nuclear recoils. And so we need this in a few different ways. The main one is the difference between an electronic recoil and a nuclear recoil. We expect that dark matter is going to bump into a really big nucleus rather than an electron, because it doesn't feel the electromagnetic force. And so it's just the size of something that's going to matter. And that's great because most of the radioactivity backgrounds are electronic recoils. They're electrons and photons that would hit electrons preferentially. So we can get rid of a lot of backgrounds if we can separate these two. Our next most common problem are alpha decays from radioactivity. And if we can tell the difference between an alpha particle, which is really a nucleus, it's the helium nucleus, if we can tell the difference between that moving in our detector and our main target material nucleus moving, that again makes sure that we can get rid of a lot of backgrounds. And finally, we want the ability to know when things are in the very middle of our detector, which is when we've shielded things, and we end up with more radioactivity around the edges. So we need to be able to know the position where the recoil happened, and our cutting out of everything around the edges in our field we call fiducialization, which means we've made some reference volume that we're going to study that we think is the best place to look for dark matter because it has the fewest backgrounds. Adding on to all of these things is that we need to be shielded from other radiogenic and cosmogenic backgrounds, which means we build our experiments down in mines and we put them inside either giant lead shields or water shields because the rock itself will generally be radioactive. So one of the things that all of our different technologies have in common is that we make very photogenic experiments. And so this is just a smattering of options in the past of different detectors to look for dark matter. There are detectors that use semiconductors and solid crystals. There are detectors that use bubble chambers. And there are detectors that use gas drift chambers. And the technology I'm going to be focusing the most on are liquid noble detectors, specifically a liquid xenon detector that's built in a cylindrical design, both like in this center one and over here, that's called a time projection chamber. You'll see why in a bit. Now this field has come really far, and you can see the types of differences in the sensitivity we're talking about. So when people were looking for the interactions that could have been a standard weak model, it was around the 10 to the minus 42 region, even a bit lower. And so early in the 2000s, a number of experiments worked there. So the different detectors we have that have a different target material are shown in different colors. We have a variety of cryogenic detectors made with germanium, some also silicon, so they're just called cryo and they're in blue. We have sodium iodide crystals that scintillate in green. We have the liquid xenon field and the liquid argon field. And so what you can see is that as a function of time, you know, we keep getting more and more sensitive. And you can see why it might be a good idea to work in the xenon field, because they have led in sensitivity historically. And I should say that this is looking for dark matter of a mass of 60 GeV. So it won't, this is, you know, selective data, so it's not quite as prominent that xenon excels if you were to look at vastly different masses. So argon can overtake at very high masses, and the lighter mass targets like germanium and silicon can dominate for very low mass dark matter. But this is sort of the history of our field, the experiments that have been really, you know, having the largest impact on the field and what their levels of sensitivity are. So what would a signal look like? Well, our field has been full of hints of signals, and I want to give you a flavor of what that looks like and why it's a little bit exciting. And they show up in a number of different ways. In many of these cases, let's start with the ones on the right, we've got some energy of the events along the x-axis and some way of telling the difference between a nuclear recoil and an electronic recoil on the y-axis. So in the CREST-2 and CDMS detectors, these are cryogenic crystal detectors. Way up high are where all of their electronic recoil backgrounds are. And in these lower bands are where they expect to see events. And events were seen at lower energies than what people were expecting. And for the most part, we think these are backgrounds. They haven't been 100% certified. Updated experiments haven't seen them. But there were unexplained low mass events that would have correlated to a dark matter particle of around 7 GeV of mass. So remember, we started off thinking it was going to be 100, and when people saw a hint, it was more at like 7. That also matched a germanium experiment called Cogent in its initial data. They both saw this slow rise is what the dark matter signal would be. So this big peak that you're like, aha, it's a signal. Nope, that's an expected background. So it's this slow rise in red. And one of the interesting things that can happen in dark matter, because there are these dark matter particles filling the halo of our galaxy and moving around randomly in our galaxy, but we aren't moving around randomly in our galaxy, we're going around the sun. And that means sometimes we're heading more into dark matter that's randomly moving, and sometimes we're moving away. And just like bugs end up dead on the front of your windshield, but not on your back end of your windshield, you could end up with more dark matter being at a high enough energy when you're moving into it. And that could give you a signal that would oscillate sinusoidally as a function of your time of the year. And so initially the Cogent experiment, and more importantly, the Dama Libra experiment in Italy, have seen this at over 13 sigma significance. Now, the reason they have to do this type of an analysis, though, is that they don't have the ability to tell the difference between the nuclear recoils and the electronic recoils. There have been many, many people that have tried to explain it, think that they've explained this signal, but for the most part, it hasn't gone away. But many, many more sensitive experiments have not seen it at all. So it's an open mystery in our field. A new open mystery just from June comes from one of these xenon experiments, the Xenon 1-ton experiment that stopped running in 2018. And it wasn't in the standard nuclear recoils that they're looking for dark matter that they saw in excess of events. But they saw it as an excess of electronic recoil events. There were more things bumping into their electrons. So these plots are a function, the energy of their events, which are the black data points, with their rate along the y-axis. And what their background model is the gray line in the back. And then in red, they can fit different other options for what means, why does their data not quite look like the gray flat line. And they're really focusing right at that threshold below 5 keV. So it could be extra tritium if there is ridiculously trace amounts. We're talking like 50 atoms in their entire tons of their detector could give you this signal. It could be a signal of a new particle that's not quite a dark matter candidate, but would be hints of brand new particles, which is the solar axion. And that was, of all these different options they studied, that was the best one. It could be an anomalous magnetic moment of the neutrino particle. And they also actually directly studied, could it be two of these adding on top of each other, tritium and a solar axion. So there's been a lot of excitement in the community. I would say that all experimentalists like me, and really like most of the Xenon 110 experiment, don't think this is the brand new exciting physics that we'd love to see. They think, you know, we've probably just not taken something normal into account. So tritium would count as a normal thing. One of the other suggestions is that there's an argon-37 decay that could happen precisely there. And that would give a monoenergetic signal at 2.8 keV, which they didn't study, but a number of other theorists have looked for brand new physics, for other things like ideas that fit on that timeline of crazy ideas like heavy photons or axion-like particles that would have single energies, and those would be, and their best fit is coming at 2.8 keV, which is where there is an atomic line from argon-37. So this is an open mystery. It means the next experiments that turn on will have something to study that's unusual. And these are the types of hints of what we're looking for in our community. So how do we actually do this in our detector? So this is the liquid xenon time projection chamber. We have a particle come in and interact within the cylinder that's filled with liquid xenon. And at that point, it makes some light. And we have light sensors at the top and bottom of the detector and reflectors along the sides. And the first bit of light we see is just a little bit, and we are not very creative, and we just call it S1. And we've got large electric fields that at the same time the light is released, some electrons get released. And those electrons are drifted up to the top of the detector by those electric fields. They actually get popped out of the liquid, and they give another scintillation signal in the gas exactly the same way a neon light works. And that gives us an S2 signal. And this whole technology is called a TPC, or time projection chamber, because we know how deep in the detector it is because of the time between these two signals. We like these two signals because S1 correlates with how much light we saw, S2 correlates with how many electrons we saw, and those ratios between each other tell us the difference between an electronic recoil and a nuclear recoil. So we deposited some energy, it hit an electron, the electron bounces and hits multiple other electrons in xenon, and we lose some energy to heat that we don't see. We lose some energy to the ionization of those electrons, and it becomes an S2 signal. And we get some excited dimers, which, you know, as a physicist, I only really had chemistry through high school, and you're told the noble elements don't make a molecule, but they can make an excited molecule. So you make this excited molecule, and then as it relaxes, you get your scintillation light, your S2. So you see, we put a lot of energy into our electrons and very little energy into our excited dimers that give us photons in the electron recoil. And I'll just flash back and forth to the nuclear recoil, and you'll see how that changes. Oops, there we go. So as you see, a lot more energy gets dumped into heat. So in general, we don't see as much signal at all for a nuclear recoil. But we've got much more equal separation of energy going into our electron S2 signal as we do into our light S1 signal. So in general, when you've got a higher ratio of light to electrons, then you knew you had a nuclear recoil, and that's the signal we're looking for. So let's see if I can flash it. Oops. So that's the end of kind of my intro to dark matter and our techniques for looking at things. So it was a good place to pause for questions now. If people have some questions.
Si alguien tiene una pregunta, la puede hacer ahora o la puede escribir. Puede ser en castellano o en inglés. Alicia. I think there's a question, Alicia. I think Victor Valera has a question. Victor, you can ask the question directly.
Thank you. Thank you for this first part. I want to know how do you, what is the criteria to define the fiducial volume of a detector?
That's a great question, and it can be different for different detectors. For the most part, we're looking for the separation of where, and you'll see this more for our particular technology moving forward, where we're dominated by backgrounds that are equal throughout the whole detector versus backgrounds that are coming from the outside. So there's always more backgrounds from the outside, and then there's kind of a flat background through the whole detector. And when you transition from those two things, that's where you usually draw your fiducial volume.
I have one question, if I may. And that is, you're showing the results by CREST and CNMS and Cogent and DAMA. And as far as I know, there's no way to reconcile them with a single type of dark matter. Right? You can take two and make it quote unquote work. You can take three maybe, but not the four of them. And now that you add xenon 1 ton to it, then not even the five of them. So is that a correct statement?
Yes, that is my understanding. In fact, it's complicated enough that the DAMA-Liebler collaboration, who has the strongest evidence, continues to say, bizarrely, that there are models for why they see something, but the xenon experiments don't. But then they don't say which of those models there are. They want a theorist to come in and separately do that. And so some theorists have. They call these models xenophobic dark matter. It's just dark matter, for the most part, that from how it interacts with its dark matter that doesn't interact with neutrons, and so are bumping into, we are expecting these scatters to be a coherent scatter with the whole nucleus. But when you really write down the particle physics of those exchanges with the nuclei, you know, it actually depends on your subatomic particles. And so you have models that it doesn't interact with neutrons. If it peaks at lower energies, so you want a lighter target, you can really contort yourself to just do that, to reconcile the, as you'll see later, we make plots that have an upper limit plot. When we make an upper limit, it's kind of a curve and we exclude everything above it. But when you see something, you make like these ovally blobs of where the dark matter could be. And all those blobs don't line up on our simplest, boring, probably wouldn't be correct anyway version of the plot. So you can try and imagine what type of physics you'd need to do to align those blobs, and that's really what the question is. And yeah, it is very hard to align all of them. it's really funny. People get, I don't know, like short-term memories. So of these experiments, as I said, Dama Libre's result is still ongoing. The Cogent experiment, as it took more data, its signal went away. It was a signal of only like 2.5 sigma significance, and that went away. But the actual crest events haven't gone away, although there is a theory among experimentalists that it could be events near the surface that the energy didn't reconstruct correctly for. The events in the CDMS silicon detector still don't have an explanation, but nobody is really pushing that they are something. Now, one of the things that they have realized affects long-term those silicon detectors is tritium. So this is that cosmic rays hitting your material can basically knock off a tritium nucleus, and then it can decay later in your detector. And so, but the rate you'd expect doesn't predict that number, but it'll affect things later. And it is kind of interesting to see that in the Xenon 1 ton experiment, that an explanation for what they saw also could be this. It would be the same story, that there was tritium created because of cosmic rays earlier on, bumping into things. And but people aren't, you know, I don't know, it's just time went on. It takes so long to run our experiments. We don't have new enough data to say anything about it anymore. And it wasn't conclusive evidence anyway. And so as experimentalists, it's like, you know, I don't have a reason to take them off my slides, but nobody's talking about it anymore. It's a bizarre experience.
We have a question in the chat from Edgar Chavarria. He asks, what would be the preferred channel for any alleged WIMP detected in XenoWIP detector? And do you have some branching ratios even from simulations?
Maybe I should open the chat too. So in our Xenon, we're looking mostly for nuclear recoils for most of the standard WIMP options. We don't really, let me see, what was the, yeah, so a channel would be these nuclear recoils. And I'll get later in my talk, I'll show what those, I'll show in our usual parameter space of measured signals what a signal would look like. I think that'll be the best answer for that question. It would look like a nucleus got hit and not an electron getting hit for our WIMP. And depending on how massive that dark matter is, it just depends how much energy those events could have.
We have a couple more questions in the chat, but we will leave them for the end of the talk.
Okay. Excellent. Thank you, guys. So I'm going to delve a little bit more now into the experiment I work on, the LZ experiment. And I should say that we're in an interesting phase right now. As I said, we're under construction and commissioning of this detector. But we also have a competing experiment. So the experiment Xenon 1 ton that has had its results out is upgrading their experiment to be called Xenon N ton. And Xenon N ton and LZ are essentially the same size and are going to be competing with each other to be the world's best experiment, which is kind of fun. And as you see, it's even a more complicated story as we go on. But this is what our detector looks like. You know, these are the largest detectors we built, and still this inner time projection chamber is only 1.5 meters tall and 1.5 meters wide. So you can see a person standing next to it by scale. That's our main detector. It's inside, it's cryogenic. The xenon is generally kept at around 165 Kelvin. So we have vacuum systems around it. Then we have a special Vito scintillator that's got gadolinium in it so that we can catch neutrons, because a neutron is the one normal piece of radioactivity that does just make a nuclear recoil, and could fake dark matter. So we want to catch as many neutrons that could possibly get into our detector, only bounce once. When they get back out of our detector, we want to capture them. So we have a veto to do that. And then we have our water tanks surrounding that, because we're deep down in a mine, and all that radioactivity is also making more gamma rays and neutrons coming at our detector. And that would be a skyrocketing rate of events if we saw that all. So we shield everything within more water. We have to bring all of our signals out, and we also have to bring our xenon in and out. We have to bring high voltage in, and we have special tubes to allow us to shoot neutrons and gamma rays come down horizontally to calibrate our detector. So this is what our detector looks like. And our main signals are based on 494 photomultiplier tubes split between the top and the bottom, as my intro slide showed. This is all located at the Sanford Underground Research Facility in a gold mine that was decommissioned in the state of South Dakota. It's now a full-time science laboratory. It's also where the big neutrino experiment Dune is going to be built in the next decade. And it is where we actually operate in a location that is called the Davis Cavern, because a physical chemist, Ray Davis, in the 1960s, realized that mines would be a good place to do science, and this is where he discovered that solar neutrinos oscillate in flavor. That was directly done in the cavern that our experiment is built in, and he received the Nobel Prize for that work. So it's an auspicious place to be working. Our precursor experiment, LUX, is what's shown in the bottom, was physically in the same location, and we're renovating that space. But our jump from LUX to LZ is a bigger jump than our competitors have gone from Xenon 1 ton to N ton. So what does the rest of the infrastructure around these types of experiments look like? Well, at our test facility stand at the SLAC National Accelerator Lab, this is what all of our gas handling and cryogenics, keeping everything cold. And so we just use liquid nitrogen because it's colder at 77 Kelvin. It can keep our liquid xenon cold. We have to handle precisely how we do that. We do that with other nitrogen gas, and then we have to take that xenon out. And part of the problem is our reflectors are Teflon, and they hold air, and everything wants to absorb an electron more than xenon does. And so air slowly will leak out of the Teflon within the xenon, and then it would gobble up our electrons. So we actually have to pull our xenon out, continuously flowing it, turn it into a gas, use a very reactive metal in something called a hot gas getter, so that everything that's not a noble gas sticks to it, and then we send the xenon back in, we re-liquefy it and put it back in our detector, so that we don't lose any of those S2 signal electrons. So that's why we have to have all this extra infrastructure to do that. So we ran a 40 kilogram test setup because we're worried about high voltage, and that's shown here on the left. And then we needed to test our full 1.5 meter high voltage parts, and that's shown on the right. And so we needed to make a very transparent grid to hold high voltage at the top and the bottom of our detector so we could drift all of those electrons. And we have to be really careful with this because long before you get a spark, you can have a couple of electrons coming off of it. But we're trying to measure just a couple of electrons, and so that would be a problem. And so we have to be really careful with these surface. And so we realized we wanted it to be made of really pure wires, and we wanted them woven together for structural strength, because under tension, we didn't want it to make the ring it's attached to kind of turn into the shape of a potato chip. So we actually made a huge loom in a clean room with little robotic arms, gluing mechanisms to weave ourselves a screen grid. And we then tested these for these high voltage. So our high voltage needs for these detectors is that we have to be able to drift our electrons so that we can tell the difference between those nuclear recoils and electronic recoils. We have to be able to pop those electrons into the gas where we get our bigger signal from. And we don't want any extra signals happening. And so what we also found is that if we use acid passivation and something we're calling training, just staying at a voltage below where it sparks for as long as possible, over time, we stop emitting as many electrons. So that's what we're going to plan to do when we turn on our grids. The type of thing that happens when we look at these detectors, we purposely put pieces of lint on a grid and turned on the high voltage. And you can see hot spots of where light is coming from. This is where we think we're emitting full electrons that are then making us our luminous signal. And then we went and we removed those dust and fibers. And you see the locations where the signals are is different, but also, you know, this was at 1,000, and now this is just at 10. And so little bits of dust, fiber from our clothes or our hair can really be a huge problem within these detectors. And we have to be really careful within our clean rooms. This is a schematic cartoon of that story of what happens in our xenon. So we have our main time projection chamber filled with xenon. We have to have our high voltage come in from the side, but then we have this weir, like a small dam, where our xenon spills over the top. We bring it out of the detector, we warm it up, we clean it, we send it back in, and we send it back into the detector. And some of this, the warmest gas, we also can remove radon, because as that air is coming out of our Teflon, it's also letting some radon out. And radon can be a big background to our experiment. And so we want to remove it as much as we can. So we have giant commercial pumps to circulate our xenon. And we try to be one of the most prepared experiments ever. And so this is our big table, our list of predicted backgrounds. And what should you get from this? You should get from this that we know what we're talking about, that we know how many backgrounds there are. And the backgrounds that mean the most, you'll see two separate columns for electronic recoils and nuclear recoils. At the top, we have all of the physical parts of our experiment and what their radioactivity could be. We have things that can be added on the surface of our detector. So this is like what dust can do in terms of backgrounds of radioactivity for a detector. We have things from the laboratory or the cosmic rays coming from the sky that we can't change. And then we have things that can contaminate our xenon. So we can clean xenon very well, except for noble gases are much harder to get. And so it's the radioactive noble gases, radon and krypton, as well as a little bit of argon, that gives us our most events. But again, luckily, they are electronic recoils. But sometimes, as you'll see, an electronic recoil can fake a nuclear recoil. Then finally, there's other things that are kind of actually real physics signals that would be there. So one of the isotopes of xenon undergoes a 2-neutrino double beta decay, xenon 136. It's exciting because people actually use this isotope to look for new physics that would be zero neutrino, neutrinoless double beta decay. That would happen at high energy, but these when the beta decay happens at low energies, we could have electronic recoil backgrounds. There's neutrinos coming at us from the sun, supernovas, and cosmic ray interactions in the atmosphere, all giving us some neutrinos. And you'll see that what happens is that some of these neutrinos can give us nuclear recoils, where they can actually interact in the same way that our dark matter could interact. So overall, we expect about 6.5 background events, only half of them really being nuclear recoils, and about 6 of them being electronic recoils that are faking a dark matter recoil. So what does this look like in terms of our spectrum? We've got all of our electronic recoils. This is out to large energies where you can see all of the different gamma lines for our different detector parts. We analyze our detector really up to only about 30 keV. So, you can't even really see on this plot where we'd stop, but you can see that, how low our backgrounds are. We've optimized for low backgrounds in the region where we're interested in doing our physics, but you can see the xenon 136, the radon, and the krypton. and our detector parts. So our detector parts fall under those lines in our area of study. For our nuclear recoils, these neutrino signals are really what the interesting story is. And so we will actually see boron-8 solar neutrino coherent neutrino nuclear interactions in our detector. And then the neutrons from the rest of our detector is what this detector plus surface plus environment line is. But dominating at low energies are solar neutrinos from boron-8. Again, I'm just showing you, these are the standard plots that get made in our field. And this is a story of what our fiducial volume looks like. So the x-axis is in r squared. So it's flattened out to have equal pixels of equal volume versus our height of our detector. And the dashed line is where we expect to draw our fiducial volume. And you can see how much we're dominated by events around the edge of the detector leaking in. On the left-hand side, it's what we just see naturally in our time projection chamber. On the right-hand side is after we apply our external veto. So that veto, we have a thin layer of xenon that we call a skin surrounding our time projection chamber. And that plus the neutron veto that can also see gamma rays reduces those backgrounds from the left-hand side to the right-hand side. And you can see how clean events are within our expected fiducial volume. Because there's gas on the top of our detector, there is less shielding, and that's why there's more events leaking in at the top of the detector. So what would a signal look like in LZ? So similar to those CREST and CDMS plots, in the liquid xenon community, we make our plots with something on the x-axis that's a proxy for energy. So this is actually just our S1 signal, and this has been corrected for any differences in light collection efficiency from different parts of the detector. And on the y-axis is the log base 10 of that S2 signal, where now we've corrected for impurities in our detector that mean that we get fewer electrons when an event happens at the bottom of the detector than the top, but we can correct that out. So that's happened here. And so a constant energy contour is kind of a curve perpendicular to these two curves. So it's not quite straight, but it's similar to that. And in blue, you see the lines of the 90% contours as well as the mean for the electronic recoils. And all those little black dots are expected backgrounds. And these would be the ones that come from the electronic recoils. In red is our expected nuclear recoil band with its contours. Then down in purple is where we expect to see the boron-8 and HEP solar neutrinos giving us coherent neutrino scattering. And they're just popping in above thresholds. So the reason we can see them is that they just end up with a random fluctuation giving them enough S1 light to trigger our detector for us to see it. And so they end up in this low location. If we were sensitive to lower energies, they would really fall within these red bands, but off the page to the left. And then what's shown in yellow and orange is the set of contours of where the events would be from a 40 GeV WIMP signal. So, so in orange is where most of those events would be, but in yellow is out to 2 sigma of where those events would fall. And traditionally in experiments, you would look just below the mean line of the nuclear recoils. You would look for events and just like count those events and see what happens. But we know that we've got enough backgrounds that some of these electronic recoils can leak down there. And so instead we use modern techniques where we put in our profile distributions for each of these different backgrounds and then look at our real data and see how it matched up. And so we do a profile likelihood ratio that is using all of the information on this plot instead of just one little window for where we look for what our signal would be. So this boron-8 signal is approximately what a 6 GeV mass WIMP would be, and like 100 GeV mass WIMP would give you signals, out to the edge of the plot. So that's kind of how the trend of how energy, how mass for the WIMP would change what the signal would be. So in our field, we give our projected sensitivity on plots that look like these, like the Nike swoosh. One day we will figure out a way to get sponsorship from them for this. But our WIMP mass is on the x-axis, and our spin-independent WIMP nucleon cross-section is on the y-axis. And so this has been normalized out so you can compare your different target nuclei to each other. In gray are particularly interesting areas of supersymmetric space where a dark matter particle could still exist once you take into account all the limits on supersymmetry that come from other physics experiments like the LHC. Green shows in this parameter space what the Xenon 1-ton result was. Black is what we expect after 1,000 days of running LZ, where our sensitivity would be. That's where, if we saw nothing, what we could rule out to. But if we could make discoveries, in the blue dotted line is where we could make a 5 sigma discovery to. In the black dotted line is where we could make a 3 sigma discovery to. And what's coming in at the bottom is something that our whole direct dark matter field is very concerned over, something that is alternatively called the neutrino floor or the neutrino discovery limit, where 7s is this coherent elastic neutrino nuclear scattering. So this is that signal where a neutrino is going to look just like dark matter. At higher energies, at 20 G, at masses of equivalent to signals related to a WIMP mass of 20 GeV, this is dominated by atmospheric neutrinos. At lower energies, it's the solar neutrinos. And you get a spike because of those monoenergetic boron 8 neutrinos. And at the level of seeing only one neutrino event, we follow this red dashed line, and you see it crosses over our expected black line. And so this is figuring out exactly where our threshold is will be highly determined if we see something like 20 boron 8 neutrinos or if we see something like 60 of them. So it will already start affecting our sensitivities to dark matter at these very low mass regions. But again, people really originally thought WIMPs were like at 100 GeV, and we're kind of optimized for 30 to 40 GeV is where our best sensitivity is. And this is almost exactly the same for the Xenon N-ton experiment, and not too different for experiments that use liquid argon. It's a lighter nucleus, it has to have a higher threshold, and so their curves start a little bit later, but actually extend out to higher energy at a slightly different curve. I find it really useful to think about what changes what that curve could look like. So on the left-hand side, we see the same axes I was just presenting. The reference limit we have is black. So let's think about what would a signal contour look like. It would look like a closed blob. And that's what we see from those experiments that said they had a signal. If we are able to, if we go to a smaller target nucleus, we shift over to the left, going from the black to the red. If we simply just increase our exposure, we go from the black to the green. And if we were able to lower our energy threshold, we go from the black to the blue. So lowering your energy threshold is always the best option you can have. If we flip this and we look now still at sensitivity, so still the same y-axis, but now the x-axis is essentially time of running your experiment or the exposure. We see that if we go from black is again our reference, we improve a little bit if we can better separate our backgrounds from our signal. That goes from black to green. If we can just build a bigger detector, we go from black to blue. So that's why we don't just keep running these detectors longer. It's really worth it to build a 10 times bigger experiment. You start improving immediately. But if we have worse backgrounds, we go from the black to the red. So that's how we think about how all these things affect our detector. Now, I've been giving you these results in this very simplified model of this spin-independent dark matter signal. And in fact, we can view it more complicated of using the real nuclear physics of these different models of how particles contract under effective field theory. So I want to quickly go through some pictures. I know we're getting to the end. I appreciate everybody being on here so long. So let's just quick see some pretty pictures in 2025, all you're going to see of our detector is the outside of a water tank like this. But what happens inside? Well, we have these grids, and you can see those wires in front of those photomultiplier tubes at the top. We have our two sets of arrays of our photomultiplier tubes. The one for the top of our detector is the one you can see, and in the back, you see the back of the bottom ones. And my group actually we have 17 kilometers of cabling because they have to come all the way out of our detector. It has to be super low radioactivity, very light mass cabling. So we have to strap it on until we can string it through later. This is that whole time projection chamber. Remember, it's about 1.5 meters tall, 1.5 meters wide. At the very top, we have to bring our, we have photomultiplier tubes looking around the edge of the skin, and so we have to bring their cables up and around. That's on the right-hand side. We have a titanium cryostat. It's lower radioactivity than things like stainless steel. And so we have the inner cryostat that holds the liquid xenon with the outer cryostat that protects it with vacuum. And we have them in place within our water tank. And then surrounding them are currently covered in white plastic are the acrylic tanks that hold the liquid scintillator for the Vito. This is the facility that's going to take krypton out of our xenon, removing one of those radioactive noble elements from our xenon so we can do our experiment. There's an idea, I'm going to skip this, but we have an idea that we could add hydrogen to our xenon experiment and then get more sensitivity. So where we expect our normal sensitivity to be is this light blue line. But if we add hydrogen to our detector and wait for the dark matter to hit the hydrogen instead of the xenon, we could go to much lower masses along these kind of orange dashed and dotted lines. So that's an option to let us compete with some other experiments as listed here. But all of this story is that it's kind of crazy. We have not turned on our experiment. Our competitors have not turned on theirs yet. We're both kind of racing to do that right now in the middle of a global pandemic. But we're also starting to think about what's the next, what's next. And our current experiments for very minimal logic that doesn't make any sense are called a second generation experiment. As I've said, we're at LZ and Xenon N-ton. You can see in the history of the funding agencies and how many experiments were before, they are not the second generation. But we would like to come together and build a detector that's about 10 times larger. That would be a G3 experiment. In Europe, this is already a proposal called Darwin. It's only about 40 tons. We're much more excited if it's more like 70 to 100 tons. You can see that these two experiments have been very competitive with each other for a long time, and we're working together now to build a new collaboration while we finish our experiments that are competing against each other. That's kind of the really kind of crazy thing that we're doing right now. But we think this is not just going to be looking for WIMP dark matter, because this is going to be pretty expensive. And we don't know that we'll be able to see dark matter. So it'd be nice to know that we can see other signals. And so there is a lot of other science we can see. So more complicated models of dark matter that I didn't get into, things that I mentioned, like under that Xenon 110 signal option of dark photons, axion-like particles. We've been talking about all of those solar neutrinos we'll start to see, supernova neutrinos we can see. We could help understand, the particle nature if we understand that Xenon 136 neutrinos double beta decay, if we can see that. And we'll also see atmospheric neutrinos. So these detectors are really sensitive detectors, and it'd be great to make one finally large enough to actually do some science with it, even if that science is maybe not quite as exciting as our search for dark matter is. So what are we going to be saying in 2025? Well, the direct detection field is going to be thriving with multiple detectors taking data over a large range of masses and signals, many more than what I've been presenting here for WIMPs. It's really a field that is growing with a lot of interest. And in 2025, I hope to say that LZ really worked wonderfully, that we're ready for this upgrade of maybe doping it with hydrogen, and that we're ready to launch our next generation detector. The exciting thing is, in post-2025, can we get to this neutrino floor? We've got kind of about I had done crazy hand-wavy calculations, a 3% chance of finding WIMP dark matter before the neutrino floor. So let's explore that whole 3%. Let's do some actual physics with neutrinos. Let's have a signal to go after. And so I'm really excited for all of those options, but to put all of this in to perspective, really all of this is just attacking one part of the puzzle of dark matter and neutrino physics, and it's really complementary to all of the other direct and indirect and collider searches and neutrino studies. And the community needs all of these things to be happening. So thank you.
Well, thank you, Professor Palladino, for this talk. We have some questions in the chat. Victor Valera asks, does LZ have the sensitivity to probe the observation of Xenon 1 ton?
Yep, and so let's go back up to this plot, exactly. So Xenon 1 ton, this is where their normal dark matter limit would be. So we can make a 5 sigma and a 3 sigma discovery of WIMP dark matter before this. If we're talking instead about their electronic recoil signals, we precisely expect, it'll be a very similar thing. So our detector is going to be about 7 times larger than Xenon 1 ton. So LZ, well, yeah. And our background rate is going to be a quarter of theirs. So, and that background rate is precisely those electronic recoils. So they see something like 60 events per ton, per ton year, and we will see about 20 events per ton year. So if there's an excess, it'll be pretty clear. One of the interesting things that can happen though is that as we told them, we think they needed to worry about argon-37, means we also have to worry about argon-37. It's a radioactive isotope that occurs after cosmic rays hit our xenon, which is what happens when our xenon is still at the surface, and it has a 30-day half-life. So after 1,000 days of running our whole experiment, there won't be any argon-37 and we'll be fine. But when we first turn on, we will definitely be seeing argon-37, and we have to wait for it to decay away to probe their electronic recoil signal.
He also asks, is the neutrino floor definitely indistinguishable?
It is at these low levels. So there's a couple of options. The best option is if you really are probing far down and can have multiple events. We talked about that annual modulation signal where because the Earth is going around the sun, we have more velocity helping events kind of above thresholds. Well, that also means that if dark matter, even though dark matter is traveling randomly, we're not traveling randomly. And so the recoil it creates will have some preferential direction. And if you can measure enough of those directions, the neutrino floor will be random and the dark matter won't. And so this is why people currently are working in the field of directional detection, because it's one of the ways to get us below the neutrino floor. The problem is one of the best ways to see those directions is by using a gas TPC. And we're building things, I'm talking about wanting to build a 100-ton detector. 100 tons of gas is really big and quite difficult to instrument and have the sensitivity that they want. So people are looking at more creative ways to do those directional studies. There is, some potential as our neutrino physics becomes more and more precise that you could imagine, if you know your number to plus or minus 3 and you see 8 more events than you expect, it's either new neutrino physics, but you have some probes potentially on what the neutrino physics is, and maybe you could say you saw dark matter. Now that's very hard, and it means something much, much bigger. It means getting like really low and getting lots of measurements. So it's not very likely. So for the most part, it's pretty indistinguishable. The nice stories though, is at the level for a G3 experiment, just seeing some of the neutrino floor becomes an actual nice signal to start doing physics with. It's sort of our point right now. So even though it limits the dark matter signal, that sensitivity we have on top of it, we can actually learn something from those neutrinos, especially the very first time we start seeing them.
We have a
Alicia, just before that, since you have the slide there, and you were just talking about it, maybe I can comment on one thing and ask you a question. So the part of the neutrino floor at energies, so WIMP masses between 100 GeV and 1000 GeV, that's where it's dominated by the diffuse supernova neutrino background and atmospheric neutrinos. And so the atmospheric neutrinos are known to within 10% the flux at best. And the DSNB we haven't even measured. So I think even though it would be nice to have a very well-known neutrino floor there, I guess it is not that well known. So this line where the neutrino floor is has a certain uncertainty to it, right?
Yes.
So you might end up hitting that neutrino floor beforehand, and if you don't factor those uncertainties in, you might claim an early discovery of something that is not dark matter. Right?
Yeah, and also, you know, we've seen this coherent scattering in, we've seen it now in 3 elements, mostly from the coherent experiment, but it hasn't been seen in xenon yet. And so if there's anything interesting happening in the nuclear physics, even these yields, there can be huge. So certainly the first time we start seeing signals here, it's definitely being taken more as understanding the signals of the neutrinos rather than dark matter. Yeah.
Right.
So what's not drawn, and that's because it's complicated, and I think we're still working on it, is where is a 3 sigma and a 5 sigma discovery line for a G3 experiment? It's not at the neutrino discovery limit line.
Right. Yeah. Okay.
So to end this section of the talk, we have, I think it's a really fun question here from Cesar. He asks, could it be possible to apply these technologies and techniques to detect dark matter from other places in outer space, maybe mining asteroids or the moon, as there would be less noise there?
Oh, that's a good question. So it's the noise though. So the types of things we get are cosmic rays, and all of those locations are probably, they're interesting for cosmic rays. There's a difference between, so we get cosmic rays because a shower builds in our atmosphere. So in those locations, you just have the primary particle, which has more energy, but because they don't build a whole shower, you get kind of different rates, but you have like no shielding at all from them. Whereas like Earth's magnetic field and atmosphere does a lot of shielding for us, and we go deep underground. And then the other thing is that the rest of this radioactivity really is coming from uranium and thorium elements that are, you know, there are just trace amounts in everything. And to my knowledge, of all these heavy rocky things would also be there. So that's kind of interesting. Now, so I don't know if it would be great to put them in space, but what other people are suggesting is putting one of these TPCs on a balloon. And there's kind of 2 different proposals for this. In fact, one of the things, our whole field of particle physics right now is undergoing a 1-year-long introspection. It's led by the US, but because the US so disproportionately leads the fields, you know, people from around the world are participating in it. We're looking at the state of the field, and in fact, talks tomorrow are going to be about this. People who want to build this type of technology to put on a balloon or a satellite or going up to the International Space Station. And what you could discover with these things could be fitting in kind of an open window in some gamma ray space in sensitivity, as well as looking for some antiparticles that, when we talked about the indirect detection of dark matter, if dark matter annihilates, it would create both the matter and antimatter. And that also happens in big astrophysical objects, but the heavier the antimatter you look for, the less likely it is to come from normal physics things. So it could be a signal of dark matter. And there's already some experiments that do this, one called AMS that's on the space station right now. Another balloon that's going to go up called GAPS. And these proposals would come like 10 years later and be even more sensitive. And you could use argon or xenon. They've got slightly different sensitivities. In many of the cases, xenon is more sensitive, but xenon is more expensive. So argon, makes up a fraction of our Earth's atmosphere. You just pull it out, and if you take it at that level, it's really cheap. So you could just use it up and not recover it. Xenon is kind of like $1,000 more per kilogram, and so you'd want to keep it. And so it means all your technology is a little bit harder. So people are thinking about putting these detectors in space on balloons and on satellites. So they're just really good particle detectors. There are people who want to put them next to nuclear reactors, so you can monitor those coherent neutrino interactions to see if any countries are like siphoning away the fissile material from a nuclear reactor. You could, people for a long time used it to try to say, hey, these would be great detectors if you're worried about radioactivity coming in at ports of entry. In the end, they're so sensitive, most of those conventional needs don't need this. But people are trying to think through other ways to use it. So not yet on an asteroid, but maybe on a balloon.
Okay, so we would like to thank Professor Palladino for today's talk. We would also like to invite everyone to next week's colloquium called Transistores de Grafeno, el futuro de los dispositivos electrónicos by Laura Serkovic from Centro Atómico de Bariloche. Thank you very much, everybody.
Thank you so much, Kim. It was a great talk.
Thank you for letting me go a little long too.
It was great. And thank you everybody for being here. See you next week. Bye-bye, everyone.
Bye.
Bye-bye, Kim.